All right. Okay. All right. So if you recall from our last lecture, which is lecture 14, at the end of this, we talk about a specific kernel called persistent scale space kernel. And it has a form that looks like where F and G are two persistent diagrams. And then we look at essentially putting a bunch of Gaussians over those sort of the pair points that is matched with one another, as well as the points that is sort of reflected along the diagonal. And then this particular kernel can be used, for example, in a kernel-based method, for example, classification, and so on. So today, we're going to move on to other type of vectorizations. So here is sort of the overview from the last lecture. If you think about the kernels, right, a kernel is a way to kind of measure similarities between persistent diagrams. And the one we focus very much on is called persistent scale space kernel. And correspondingly, there's three other kernels that has been published in the literature, specifically persistence weighted Gaussian kernel. So it has a similarity with the persistent scale space because it's again using Gaussian kernel as a part of the construction. There's also what's called slice Washington kernel and also persistent Fisher kernel. So they are all implemented in the sklearn TDA package. So, I encourage you to go play with the code and to see what they do. So that's one way to think about how to compare persistent diagram in terms of comparative measure based on kernel. There's also other ways of what's called vectorization, right? And then we are going to begin today's lecture talking about one form of vectorization, which is persistence image, which is essentially saying that I'm going to take a persistent diagram and convert it to an actual image. So if you think about an image is essentially a matrix. Once you represent it as a matrix, you can just concatenate, for example, each rows together. That became a vector. And then you can use it again for downstream analysis. So we are going to talk about primarily persistence image. And then next lecture, we're going to also start talking about another version, which is persistent landscape, which is converting a persistent diagram into, again, a collection of numbers, of vectors, but by treating it as first as a collection of one-dimensional functions. Okay. So that's sort of the overview of sort of how what we're going to cover over the next few lectures. So today, what we're going to start with is one of those vectorization, which is called persistence image. Okay, so the high-level picture is as follows. If you have data, in this case, say a scalar field data or a point cloud data, we know that if we can impose a filtration over this data, we can compute its corresponding persistent diagram. Okay, so the second picture here is my persistent diagram in the classic form, where remember each point in the diagram corresponding to the burst time and death time of a particular feature. Of course, whenever we talk about persistent diagram, remember we always talk about zero-dimensional feature, one-dimensional feature, and sort of p-dimensional feature, where p bigger or equal to 2, for example. Right. So each time, remember, when we are actually talking about persistent diagram, we're not combining the dimension, right? Because when all the distances we have talked about so far, bottleneck distances, Washington distances, is always compare persistent diagram of the same dimension. The same thing with the kernel we have been talking about so far, that the kernel is defined of persistent diagram of the same dimension. So, from a sort of intuitive perspective, you always want to compare their dimensional feature against their dimensional feature, one-dimensional feature against one-dimensional feature, because, when you talk about bottleneck distances, what you're inherently trying to do is to match zero-dimensional feature against zero-dimensional feature, one-dimensional feature against one-dimensional feature, because it makes zero sense for me to match a zero-dimensional feature against a one-dimensional feature, right? So it's always done through a fixed dimension. So now, if you have this, what is a rough idea of a persistent image, right? So we want to transform the persistent diagram now to be some vectors. The way to do it is essentially kind of based on the density of my points in the persistent diagram. So the first thing, after I have the persistent diagram, the first thing that is happening is actually rotated by 45 degrees, okay? So the reason why is because we want to turn it into sort of a square image, okay? So because the classic persistent diagram we have been talking about, there's no point in this quadrant, right? So what we want to do is to say, let's just focus on the area where there is information. So when you rotate it 45 degrees, you got the third picture. Okay, this is a rotated persistent diagram. And what's interesting about it now is what we're seeing is that the x-axis of this rotated diagram is the burst time of the point. And then the y-axis now, right, if you imagine what's happening, and in this particular transformation, is that the y-axis now is basically the burst time, the death time minus the burst time. So to be a little bit more accurate, this transformation goes from each point, which has a burst time, death time, to burst time, death time minus burst time, okay? So what this means is that the height of each point now is a persistence. So when I say it's rotated 45 degrees, I'm not exactly being accurate, because if you look at this diagram, this distance is actually burst time, death time minus burst time, right? But when this transformation is trying to say that, okay, now my x-axis is the burst time and my y-axis is the death minus burst. Okay, so essentially how far the point is from the x-axis, it tells me how important it is. Okay, so now what's happening is that after you have rotated and you have performed this exact transformation, what you're going to do is you're going to put some function that on top of each point and sum them together. And then the rule of it is to say that for points that has a high persistence, I'm going to put, in some sense, a bigger bump, versus points that has low persistence, I'm going to put a smaller bump. Because the reason I'm using the word bump, you will know that by default, what I want to do is I want to put a Gaussian over each of the points in my transform diagram. Okay, so if you see here, the sort of bright color corresponding to high function value. So this point right here that has one of the highest persistence, right, which is this point here, it's actually showing to be very bright because I put a much larger function there, where the scale of that function is proportional to its persistence. And now the next step you do is, once you turn this into sort of a mixture, in this case, a mixture of Gaussian, the next step you do is to try to make it into a discretized form. So when I say discretization, I'm going to impose a discretization of the image into different resolution. Okay, so if you look at the bottom one is a finite resolution. Let's say it's 128 by 128. Okay, so the second one may be 64 by 64, and the next one may be 8 by 8. Okay, so you have a different way to try to discretize it. And when you discretize it, you kind of just look at the average value in that grid. Okay, making sense so far? Okay, so now let's say if I discretize it, let's say this is roughly 8 by 8. Actually, it looks like maybe, yeah. Let's say this is an 8 by 8, right? So what did that mean? That means I have converted my original persistent diagram into a vector that is size of 64. Okay. So what is a formulation? Okay. So first of all, we define symmetric, normalized symmetric Gaussian, whose mean is at a particular point and whose variance is defined by sigma square. Then at a particular location, any location in my domain, the evaluation of the Gaussian has this form, right? So it's basically looking at, this inside term is a distance, Euclidean distance squared to this center point of the Gaussian, right? And then there's some scaling parameters, right? So in a sense that if I have a two-dimensional domain, let's say this is the center of a Gaussian where I'm putting it, this formula is, so this is ux, uy, this is the center of the Gaussian where I'm putting it. And what I'm doing here is for any point x, y, I can evaluate the influence of this Gaussian on this point, okay? So now, if we have a non-negative function defined on the domain, which is called f, and let's say it's 0 along the horizontal axis, it's continuous and piecewise differentiable, right? So it's a nice, well-behaved function and non-negative. Then if I have a persistent diagram, then we can talk about the persistent surface. So this is a persistent surface, which is a fourth picture. It's basically a sum of, so a sum of the rotated persistent diagram. For every single point in the persistent diagram, there is a function times some form of kernel looking thing, and that became my persistent surface, okay? So what is those two things? And we're going to be clear next in the next slide. But what this is doing is to say for every single point in my rotated persistent diagram, I'm going to look at a mixture of function that is centered around those points, okay? And then if we try to discretize it, if we fix over a grid with n boxes or n pixels, in the previous example, this is 64 pixels. What we're doing is to, for each of this box or each of this pixel, we're going to just assign the integral of this formulation, okay, over that region. So what is the form that they actually used? Sorry. The form they actually used here is that they're replacing essentially, well, why am I missing a picture here? I think I did missing a picture. Sorry, apologies. What this picture does here, actually it will come back to me later, is that this weighting function is now, right, the weighting function is now this Gaussian function. And I believe, if I remember correctly, the second term is the one that has to do with the persistence, which is P, just a second, which is the death minus birth, okay? So just give me a second because I think I lost a slide. So just a second. So okay, so I did the other way around. So let me be clear. So let me change it the other way around. Actually, the first one is the weighting function, and the second one is a kernel. Okay, that makes sense now. So what happened is that the weights has to do with the persistence. Okay, so one way they do is that So I'm going to add a new slide since I missed that slides. So one way they do is they specify, so remember I need to have a weighting function. So this is a weighting function. And then this weights has to do with the sort of the persistence. So what they define is to say for a particular point in the rotated diagram, the weights is equal to related to the y-axis. Remember the x-axis is the burst time and y-axis is the persistence. So in this case, the weight has to do with the y-axis, which is the persistence. And the way it's defined is to say that, you know, this function is equal to 0 if the persistence is 0, or, you know, of course, it cannot be less than 0 in our situation. So it's 0, or it's its persistence ratio with respect to the birth. Okay. So, and then it's 1 if okay. So what does this do, right? This weight term, the first term, is roughly trying to capture the importance of the points with respect to its persistence, but it's do it in a very sort of normalized way. What happened is to say that, okay, if the point is exactly on the diagonal, I know that I don't want to put any importance to them because those are zero, those are sort of zero persistence points, right? That means they are born and die right away. So they are not going to have any contribution. But then when I have non-zero persistence, there's two scenarios. One, if my persistence, remember in the actual scenario, this t is really death time minus burst time, okay? So when it says if the persistence is bigger than the burst time, okay? So essentially I want to put a sort of a scaling factor to say that, well, if it's, if the persistence value is bigger than the burst time, what does that mean? That means this is bigger than burst time. That means the death time is at least twice the burst time. This is really what it means. It means that, you know, somehow it lasted quite a bit of long time. Then what we want to say is that it has a weight of 1. And then if I'm in between 0 and then burst time, so essentially my persistence is a fraction of the burst time, then this is taking the persistence, which is again, right? This is taking the ratio between the persistence and the birth, okay? So this is a particular scaling to say that I want to put a high weight to points with high persistence, you know, so that's what gives those sort of highlighted points, is because those points are in some sense more important than the points at the bottom, okay? But of course, the interesting bit is that in the actual theoretical work, when they actually talk about this particular formulation, is one of the driving force behind this definition is ultimately they still want some sort of stability, meaning that if I perturb a little bit over my underlying persistent diagram, I want my persistent image to also just perturb a little bit, maybe at a fixed resolution, okay? So again, as you see so far, even with vectorization, one of the very important quality we want to have is that is to have some form of stability so that I can use it for classification tasks, okay? So now the second thing is, you know, the term that is the second term, right? And this second term is essentially what sort of kernel we want to put over a point in the two-dimensional domain. And in this case, the specific kernel that's used is this Gaussian kernel. Okay, so another way to really mentally imagine it is that if this is my rotated persistent diagram with a bunch of points, you are essentially putting sort of a scaled Gaussian over them and sum them all together. And that's what you have in terms of persistent image. Okay,
So before you put the Gaussian in the image, is it like a pixel is bright if there's a point on that in the original persistence diagram and
Yeah,
dark
so
if there's no?
right. So if you look at this formula, right? Let me just erase this so it's not too confusing. What's happened, right, is that the first term is a weight term. Is to say how important do I want this particular point to be? Okay, right. That's the first thing. The second term is what is the shape of the kernel function I want to put on that point. Okay, so going back to your question is that remember this function is what's called persistent surface, is evaluated over every single point z that is in the two-dimensional square, right? Two-dimensional domain. So for every single point, it's going to have multiple. In this case, let's say if I'm using Gaussian as my kernel function, every single point is to have multiple Gaussian that's going to influence the value of that point. Is that making sense so far?
Yes.
So basically, again, let me just draw a really nice picture, is that let's say I have, this is my sort of, I'm treating this, I want to draw it as a terrain, right? So this is my rotated persistent diagram. And let's, for the time being, let's say there's just 3 points off the diagonal, okay? Now, the way I do it is that, so those points are the points U in my rotated persistent diagram. So this is U1, this is U2, this is U3, okay? But then for every single point Z that is in the domain, let's say right here, let me just use a different color. Let's say this point Z, right? It's going to be influenced, the function value at the point Z is going to be influenced by the function that is put on top of each of those persistent diagram point. So what happened is that because I put it a weighted Gaussian over here, right? Think about it. There's a bump here, there's another bump, and there's another bump, okay? And whenever you do this, it's the behavior of Z is a sum of influence of those 3 Gaussian kernels. Okay, so if you look at the formulation here, the row B at Z is going to be sum of U is in the set U1, U2, U3, right? Those are the 3 points in my persistent diagram. And it's going to be the weighted version. So there's some sort of weights, F of UI, F of U, okay? F of U, because U is a point, so each point is going to have a weight. And in this case, it's a Gaussian, so it's GU of Z. So what does this mean? If I spelled it out, is actually equal to F of U1 times GU1 Z, F of U2 at GU2 Z, and plus F of U3 and GU3 Z. Remember, GU of Z is a Gaussian kernel. So what is this saying is that I have a kernel that is defined on this point, and I'm evaluating the function value at Z with respect to this center. And then essentially you're looking at the influence of the Gaussian kernel at U1 over Z, influence of a Gaussian kernel of U2 over Z, and influence of a Gaussian kernel over at U3 over Z. So okay, that is what your persistent surface looks like.
And F is larger depending on the lifetime of that feature.
Exactly. So for example, if I move my Z close to here, let's say I move another point, let's say this point is Z prime. If at my Z prime, because it's closer to this U1, and because U1 has high persistence, this kernel has have a larger weights, right? So that's why you are seeing a very bright region over there. But if I have another point, say Z double prime, that is close to the x-axis, then the influence from the bigger bump is much smaller. So you have a lower, function value. So we're talking about points here versus points here.
Okay.
Okay. Another way to really think about it is really this function, this function here is a mixture of Gaussian, but it's a mixture of weighted Gaussian function where the Gaussians are centered around points in the persistent diagram. Okay, so for that matter, if you look at this two form, this persistent image has a lot of similarity with scale space kernel, right? Because scale space kernel, again, is trying to put sort of Gaussian bumps into places and sum them all together, but they're doing it in a slightly different way. Okay. All right. So now, sorry, go ahead.
Is the sigma like hyperparameter that you have to tune?
Yes.
Okay.
Yes. So yeah. So you will have a parameter to work with. The same way with persistent scale space kernel, right? You have this parameter.
Okay. Thanks.
Yeah. So okay. So what's the usage of a persistent image? Remember, again, when I vectorize it, my goal is to do classification. So this is a classic example from the original paper. Oops. Okay, hopefully my battery will last. Is that, you know, without looking at the underneath, you know, caption, what is what is sort of the classification of those images, right? So those are some form of synthetic images that are generated by different parameters. Okay, so if you look at it without looking at the underlying parameter, the idea is, let's say I have those 5 different images, and they are all generated by small variation of underlying parameter. The question is that, can you actually classify them based on their underlying parameter? Okay, so in the original paper, there is an equation they use to actually synthetically generate this example. And the equation they have is quite involved. Let's see if I can write it out. I kind of ignored it initially. Just a second. Let's see if we can find it. Yes. So it actually has to do with what's called surface dynamics. Okay, so surface dynamics is sort of like a partial differential equation, and if you are curious, it's some sort of PDEs. So the bottom line is that it's a closed form solution of a PDE. Okay, so this is really the closed form description of how to generate those images. But what's happened here is that really there is a parameter R in this formula. As I change R, you can think that, you know, I generate different surface patterns. So if I'm just eyeballing, right, it's fairly difficult to tell the difference between those images. It almost looks like they come from the same generating parameter R, okay? But it turns out if you're using persistent image based way, basically you try to compute what is the persistent diagram associated with each of those images. And of course, you have different ways of introduce a filtration, which is very similar for our mini project, right? So our mini project is to say, if you give your image, how can you build a filtration in order to compute persistent diagram? For example, in this case, obvious filtration is what's based on, say, sub-level set function, right? I'm treating each of the image as a scalar function, and I'm looking at the sub-level set of that function as my filtration, and I can get my persistent diagram. Of course, there's other ways to generate it. So the idea is that if I have the persistent diagram generated from those 5 images, I would like to use sort of my persistent image to classify them. And what is the idea is that, for example, let's say I fix a resolution of my persistent image. Let's say I'm always using 64 pixel, a length of 64 for a persistent image. Then the idea is, if the images were generated by the same parameter, then the corresponding persistent image should be close. Versus if they are generated by different parameter, right? Their corresponding persistent images should be far away, right? And in this case, the distance between the persistent image is well defined because you turn into a vector. So you can use, for example, cosine distances, or you can use things like Euclidean distances. Okay, So in this particular case, it turns out is that, well, this is answer is upside down, right? So it turns out the first image is generated by R is equal to 1.75. The second one is 2. This is 1.75 and 2 and 2, right? So in this case, you know the first and the third image, their corresponding persistent image is closer than from the second and fourth and fifth images. Okay, so this is really a classic example how persistence image can be used in classification tasks. Okay, so of course, my follow-up question, which I think would be an interesting take home, is that there's other ways to vectorize persistence diagram. And we're going to see one more in the next lecture, which is persistence landscape, okay? So the question is, if I change the different ways to vectorize my persistence diagram, is it going to influence my classification results, right? So in a sense that if I use a different way to vectorize my persistence diagram, do I get the same classification results, or I cannot achieve the same type of accuracy, right? So that's the first question. So if I change to a different vectorization, okay? Of course, the second question is, what if I use kernel, right? Remember kernels that we learned, and there's 4 of them. We only went through detail for 1 of them, right? If I'm just using kernels, is that going to tell me a similar thing? Like, for example, if I fit my kernel into, say, kernel-based SVM, is that going to also separate those 2 classes? Okay, so that would be the conjecture, how much differences are there among different kernel methods and how much differences are there among different vectorization schemes. Okay. All right, any more questions?
Yeah, I have a question about the last example for this. It seemed like your weighting function was, because it was based on birth. Like if you go to that
this slide?
I guess the slide before it. Well, yeah, I guess it's based on the weighting function itself. It seems like it would be skewed to the left because it's based on the birth time, right? And the
no, it's actually based on both.
Well, okay.
So B is a birth time. T is persistence. So T in here, T is death time minus birth time.
Yeah.
So,
and I guess because T divided by B, it seems like for the higher birth times, the weighting function would always be lower, even if the persistence is the same, even if it persists for, say, 2 time units. On the right side, because the birth is higher, it would be scaled lower. And so it would kind of skew the other way.
Yeah, I wouldn't use the word skew, but I think I get what you're getting at. Is part of this is that there is actually understanding, and to be fair, the persistence over birth, this is not the only place this formula shows up. I think I can later on, if I find the references, I can put it in the shared reading list. This particular formula actually show up in some other research papers. When people are studying persistence diagram, the argument is actually, if I have a feature that is born earlier, I would like to put more importance to it. That is really the argument. Okay, so in some sense, yes, if you're using the word skewed, it's skewed towards the features that is born earlier. Okay, so when does this thing become larger, right? In this threshold is if I have a feature that is born earlier and have a high persistence, that will be something that has a higher weight, right?
Yeah.
Now, that's exactly what this formula is trying to do, right?
Okay.
But of course, it's also trying to cap it a little bit. It's if you look at the last bit of the range, it says that if somehow my persistence is like at least more than twice the burst time, then I'm going to cap it at 1, right? This is just to try to prevent it's actually try to put an upper threshold to this weighting scheme so that the weight is always between 0 and 1.
Okay.
Yeah,
that makes sense. I guess in in different weighting functions, I guess how common is this weighting function in general, or how like diverse are the weighting functions?
Yeah, so in the original paper, right? So this paper is in one of our reading list, and also it's mentioned in this reference right here. The idea about this particular weighting scheme is trying to talk about stability. So it's all actually driven by stability argument. Is to say that, okay, what sort of weighting scheme can I do such that I can actually still have a stable comparison, right? So actually, the stability is in a very is basically in section 5 of the entire paper, where they actually talk about the stability of the persistent surface and the stability of the corresponding persistent image using this particular weighting scheme.
Gotcha.
So put it other way, maybe you can change the weighting scheme, but if you change the weighting scheme, you need to also prove that it's stable.
Yeah.
Yeah.
Okay. Cool. Thank you.
Yeah. So, all right. Okay. So that's that's one use of persistent image. And now I'm going to take a step back because I talk about a few kernel methods already. One of them is a kernel perceptron algorithm, right? But another one that is used very widely is SVM and kernel SVM. So again, I want to talk about the sort of the philosophy behind SVM and kernel SVM, with understanding that what we are going to do is you can kind of interface the kernel between persistent diagram with those kernel-based methods, right? SVM is a nice example because it's what I would argue a very interpretable classification tool, right? So we're going to spend some time talking about SVM and kernel SVM. And I think I'm going to take a 5 minutes break. This is a good time. And then feel free to ask me questions. Otherwise, I will see you at 9:53, 5 minutes break. All right. Okay, so now hopefully folks are back. Let's talk about SVM and kernel SVM. Okay, so SVM stand for support vector machine, and it's one of those very well-known classifiers. And the idea is to try to separate a training point with respect to the maximal margin. Okay, so what is the margin? The margin is a distance to the nearest training point of any class. So in this case, if the margin increases, the arrow decreases. So in some sense that when we think about the perceptron, as we sort of discussed a few lectures ago, it does not optimize the separation distance while SVM does. Okay, so in this particular case, if you think about, I have, again, we're talking about linear classifications. I have the class that is blue and then the class that is red. And I'm looking at sort of linear separators between them, which are my classifiers. Okay, so in this case, if I have L1, L2, and L3, what's really interesting is that, well, L1, for good reasons, it's not a very good classifier because it does not separate the blue class from the red class, okay? But L2 and L3 both has a separation between those classes. But however, L2 has a smaller margin than L3. Okay, so what is a margin? Margin is sort of the distance to the nearest training point. So in this case, we will argue that L3 is actually my desirable separator versus L2. Okay, so but what is the formulation? The formulation is the following: is that let's say I have training data, in this case, a bunch of two-dimensional points, and then they have a corresponding label. So the X corresponding to the coordinates and Y corresponding to its label. So the label is either +1 or -1. And the idea for SVM is to maximize the margin, which is this line, and then this is, in higher dimension, is going to be a hyperplane. And you want to maximize the margin that separate the training data between plus and minus labels, okay? So what is a margin? Is the distance between the hyperplane and the nearest point. So in this case, the nearest point for, let's say the blue class is this point, and this is the margin, okay? And the second one, the nearest point is this highlighted red point, and this is the margin. So this is the distance is a margin, okay? And we would like to maximize this margin, okay? And then the supporting vector are the points on the margin, which is those points that is closest to the hyperplane, okay? And now if you look at this, if you look at the margin for L2, L3, it's this distance and this distance. But then if you look at L2, the margin is going to be this distance and this distance, okay? So what support vector machine do is trying to maximize this margin. Therefore, it's going to choose L3 versus L2. Okay. So some part of this is very, this is a spelling mistake. Some part of the SVM looks a little bit similar to the perceptron, because remember, perceptron is trying to shift this, this linear classifier so that it's optimized some function. It's the same thing here, where we're trying to move the linear separator to maximize the margin, okay? So what's going to happen is that if I move those points, which are the supporting vectors, it's going to change the margin, right? But if I move those points, that is not the supporting vector, it's not going to affect the margin, and it's not going to affect the decision boundary. So in some sense, it's called supporting vector machine, is that those supporting vectors that decide what the margin is are much more important to decide the decision boundary, okay? So now, again, we're going to go a little bit into the math, right? So same thing as before. In order to define this linear classifier, I am going to define a normal direction W. and that W, and also how it's related to sort of the origin, right? The intersection with origin fully describe my separating hyperplane. In this case, it's a line, okay? So now you have basically two parameters. You have the normal vector W, and you have what's called the offset, right? So this sort of defined what this decision boundary is. And now what's happening is that, of course, this line is when Wx minus b is equal to 0. And then this two parallel line that is, away from this is exactly sort of has to do with then when this line is equal to 1 versus this line is equal to -1. Okay. So what do I do? There's, of course, there's multiple versions of my SVM. So the first version is called I have hard merging. Okay. So first of all, if I assume my training data is linearly separable, right? So what's a linear separable? If I have data like this is not a, well, let's put it a few more points. This is a data that is not linearly separable. Okay, so first of all, we assume they are linearly separable, and then there's some sort of constraint that for every single point in my data is that this separating plane Wx minus b is bigger or equal to 0 if it has, positive label, is less than equal to -0 if it has a negative label, right? So in sort of geometric terms, sorry, just a second. I think my screen just hung. Okay, so it's just to say that the point that has a positive label or negative label is sort of a little bit away from my decision boundary, right? In this particular picture, they are either Wx minus b is either bigger or equal to 1 or smaller or equal to -1. So now the argument is that every single training point we use have to lie on the correct side of the margin. And the constraint, right, which is what it should satisfy once I find this separator, is for every single point its label times the formula that decide on the decision boundary is bigger or equal to 0, right? This is not surprising because remember, if it's a negative label, this is the first term is negative, second term is negative, right? So basically this thing is just translating this constraint, rewriting the constraint in a multiplicative form, okay? So the idea is for the SVM, what it's trying to do is try to minimize this norm of this W subject to the constraint. So what is this norm of this? If I minimize, so if you look at this thing, if I minimize the norm of W, it's maximizing this sort of gap between the two classes, right? So essentially when I say maximize the margin, it's corresponding to minimizing the norm vector. So that's how it's, right? So again, maximizing margin is subject to this. So minimizing the norm is equivalent to maximize the margin because the margin is 2 over the norm, okay? All right, so now we are going to try to solve the optimization problems, and then let's say the optimal solution is W star and B star, which is the optimal parameters that decide my decision boundary. Once you have that, then every single point is going to assign a label that is based on the sign of Wx. Okay, so that is what's called a hard margin, right? So hard margin is trying to sort of maximize the margin. Well, sorry, twice the margin or 1 time. So the margin is 1 over, and then this 2 times is twice the margin, right? So remember, this is a margin. So the hard margin is try to maximize the margin, which corresponds to minimizing the norm of the linear separator. Then there's also a version of what's called a soft margin. And in this case, that assume that the training data is not linearly separable, then there is a little bit tricky thing to do is to define what's called a hinge loss. So what hinge loss do is for a particular points, the loss is a maximum between 0 versus 1 minus this multiplicative term. Okay, so essentially just to say how far away of my points from, again, the decision boundary. Okay, so in this new form, right, because you are assuming that they may not be linearly separable, but we're just going to, in some sense, on a very high level, is to measuring how far away it is from being linearly separable. So in a sense that the minimization now become minimization of a particular loss function, which is for every single point, right? There's a normalization and sum over all every single point. We're looking at this loss function. So this is CI plus a regularization term. So this regularization term is sort of lambda. Again, this is a hyperparameter with respect to the W. So now, so the lambda, another way to think about it is try to have a trade-off between increasing the margin and ensure that my data point lies on the correct side, right? So try to minimize this sum is have a balance between sort of having a, because I'm minimizing, when I'm minimizing W norm, I'm maximizing margin. So in this formulation, I'm still partially aiming to maximize the margin, but with a constraint that my data is lie as much as possible on the correct side, okay? Because my data is not linearly separable. So so now if lambda is very small, then this became negligible, so that this is going to change to a hard margin problem. Okay. So now there is, okay, so far any questions, right? So this is again a high level picture of how does SVM works, but then there's another perspective of looking at SVM, which is called the primal and dual perspective. So if you look at, again, the loss function, it's taking the maximum between 0 and how much it can be linearly separable. This is the smallest non-negative number that satisfies the condition that this is bigger or equal to 1 minus CI. So what is this doing, right? Remember, in the hard margin scenario, the constraint is that the label times this sort of weighting scheme is bigger or equal to 1. But because my data is not linearly separable, the version we just see, so let me just write it out. So the hard margin is the situation I'm requiring, the constraint I have is this has to be bigger or equal to 1. But the soft margin is essentially saying that it's almost bigger or equal to 1 with a little bit tolerance, which is this cost function, right? So it's just to say that I would like it to be as linearly separable as possible, but with some tolerance. So now, if you again looking at the, what's the optimization problem, it's try to minimize this term subject to this constraint for all data points, right? So that is how the soft margin is formulated. I mean, this is exactly this formula, just I'm replacing this by CI. Okay, so there's sort of a loss. I want to minimize the loss plus a constraint over minimization of also W, the norm of W. Okay, so now this is a primal version. The dual version is to rewrite this optimization. So this is a minimization problem, but I can change it to a maximization problem. Okay, so the dual version of it is turning a minimization to a maximization. So the dual version is a maximization problem, is to maximize, this is a complete rewrite. It's to maximize a function that takes all this individual loss, right? And then this function is essentially the sum of individual loss minus, this double sum of taking the dot product of xi, xj, and so on. So everything I'm writing out so far, you can kind of try to derive it mathematically later. But at this moment, just trust me that I could rewrite this entire formulation from a minimization to a maximization. So what does this maximization do is it's maximizing this function, which takes input as individual loss, with subject to the constraint that the sum of those loss times the label is equal to 0. And this loss is somewhat between 0 and a number and an upper bound. Okay. So assuming that you trust me, this is how the dual maximization problem is an equivalent thing by if I maximize this function is equivalent to minimize this function. What we have is we can turn the SVM into what's called a quadratic programming based on each of the individual loss subject to this linear constraint. Okay, so now if you are looking at the dual space, which is maximizing this this function f, then you can actually write it out you can actually solve it by quadratic programming. But then based on this dual and primal formulation, you will see that number one, the W parameter is now a linear sum of the cost times label times the coordinates. Okay. And then if SI is a support vector, remember what's a support vector? The support vector are the ones that decides on the margin. The support vector is if SI is support vector, then it will satisfy the condition that if the support vector has satisfied this condition is equal, it implies that I have, this is just a translation of it for any support vector is satisfy this equation. Okay. So, well, a little bit over quadratic programming. So what is the general formulation of quadratic programming? If you have n variable and you have m constraint, then you can say, okay, what I have a few sort of matrices where C is a vector, Q is a matrix, A is another matrix, and B is a real valued vector. The idea is to try to find a solution X, which is n-dimensional vector, that minimize a form like this. Okay, so this is sort of the most generic form of quadratic programming. And you can see that, and one of those ways to solve this general, so this is sort of a little bit divergence towards numerical algorithms or scientific computing. One of the way to try to find the minimizing term for this for this objective function is things like conjugate gradient, right? So, so if you're unfamiliar with conjugate gradient, I would suggest you just read quickly the Wikipedia page. But the idea is because I want to sort of minimize this, right? If you imagine this whole function as a landscape, what you're doing is you start with some random position. Let's say I start with a random position x0. The idea is I'm going to walk in the direction of the fastest gradient descent direction, and I walk for a small period of time and readjust in that location to say the next direction, which has the fastest decreasing in terms of faster decrease in terms of function value, which is sort of the gradient direction, and walk in that direction for a period of time. So in this way, what the conjugate gradient or any sort of a tracing gradient method is trying to say take small walks towards a decreasing function value, which at the end point you are going to end with a local minimum. Okay, so again, a very intuitive or animated view is imagine you are an ant. This is sort of a local minimum, right? So if I picture this from a 3D perspective, is that those are all the contour lines. Well, not the best plot. Let me write it this way. What you're seeing here, those contour lines are the ones with the same function value. And then this is a local minimum. And you have all these contour lines. Okay. Okay, and what you have is you say, I'm going to start with a random position, right? This is my x point. And then some random position x0, and conjugate gradient or the other similar method, what they do is to say, at this location, I know exactly where my gradient direction is, and I'm going to walk in that gradient direction for a small period of time. And in this case, depends on which formulation you use. The step size is sort of is a parameter you can tune. But let's say I walk a little bit over this direction and end up in a new direction. And as I walk in this direction for a period of time, end up in a new direction, I know my gradient direction will change locally. So I'm going to readjust the local direction again and walk in that direction for a period of time, and so on and so forth. So at the end of the day, when this converges, you are ending at a local minimum. It does not guarantee you are always going to end with a global minimum, but as in this particular case, depends on your random starting location, you might end up with a different local minimum, right? So in some sense, you can have random restarts to try to find what is a minimizer for this. Okay, so that's a high-level picture of SVM. So what is the takeaway? SVM is sort of maximized margin, and it has a hard margin and a soft margin version. And on top of it, it have a dual perspective, right? Or for sort of maximized margin, you can translate it to a minimization problem or a maximization problem. Okay. So now we know that a subset of the training data points are going to be support vectors. Those are the vectors that define the margin. Okay. So SVM, then the decision boundary, which is a linear line or hyperplane, the norm direction can be written as a linear combination of the support vector. Okay, this is what we just seen, is that the W vector can be formulated as a linear combination, a weighted linear combination of the support vectors. Okay, so now what is a kernel SVM? Okay, kernel SVM is in the sense where I'm going to rewrite the separator in the transform space. Remember our kernel method, this is exactly the same as before. If I have data that is not linearly separable, if I transform them to a feature space, they become linearly separable. Okay, so kernel SVM is basically running the linear SVM in the mapped space. Okay, so in this case, what's going to happen, this map phi transform my original support vector into the feature space. Then what I'm defining here, this is now a linear separator in the feature space. All right. So now what is a kernel? This is what we have talked about before. This kernel is defined as the dot product of the corresponding transformations. Okay. Any questions so far? Right. The only difference between, in some sense, between SVM and kernel SVM is think about SVM as trying to find a linear classifier in the original data space, versus kernel SVM is trying to find a linear separator in the transform space, which is called feature space. Okay, right? So in this case, my support vector is also transformed into that space. Okay. So now with kernel SVM, I'm also going to have a primal and dual. The only difference, right, if you look at this formulation, in the previous formulation, the dual version in this red is just a dot product between the two vectors, okay? Now in the kernel space, the dual form of kernel SVM is just replacing S1 Si dot Sj by the kernel between Xi, Xj, right? So in this case, it's just the similarities between these two vectors. Okay, and everything else stays the same. And now you can also do quadratic programming again, right? You just replace the corresponding term by the transformed term with the transformation map. So if you look at the formulation here, in the previously, you are looking at, yi times xi, what you do is you replace that by yi times the transformed xi. Okay, and then b is equal to w of transformed support vector versus previously b is equal to w times just the support vector. Okay, so this is all actually very straightforward. And but why do I even insert this piece of content here? Now imagine what I'm doing here is that my points in the picture that I showed, now imagine the points that each of those points is a persistent diagram. Okay. Then what you're going to do is you are going to run kernel SVM, where the kernel is, for example, persistent scale space kernel. And now you can just apply kernel-based SVM over a collection of persistent diagram. You can do the same thing. And like I said, kernel SVM and SVM are one of those very commonly used classifiers. So you can imagine you can use kernel SVM to classify persistent diagrams. Okay. All right. Right. So all you need to do is to replace the kernel here, where xi, xj are now, each of them is a persistent diagram. You just replace this by the corresponding kernel on the persistent diagram. Okay. All right. So now I want to mention a bit over deep learning with topological features. So remember at the beginning of the semester, we spent some time to talk about how sort of topological features can be interfaced with machine learning. We gave some examples. And this is sort of a continuation of that. And I'm going to talk about specific papers that, that uses topological features in machine learning. And this is a particular paper in 2017. This is slightly different than what we've seen so far, right? The one way to interface persistent diagram with machine learning is to say, okay, I can use kernel method. I can look at kernels between persistent diagram. Then I can do kernel SVM. I can do kernel perceptron. The second example is I can take persistent diagram and vectorize it into a vector. And then I can measure distances between the vectors. And then that can be used again for clustering and classification. That is in the example of persistence image. So this particular example sits somewhere in between. It's not exactly vectorizing it. It's just to say that I would like to transform a persistent diagram into, again, a bunch of numbers. But it's not the exactly same way as persistent image, even though there are some similarities between them. Okay. So the main idea for this is to transform the persistent diagram into as an input layer to be used by neural network. Okay. So what does this do? So again, the first picture here is a persistent diagram, classic persistent diagram, where every single point is a burst time and a death time. Okay. So, and now what it's going to do is that somehow we want to take information from the persistent diagram, and through what they call an input layer, it has multiple parameters. And then the end result is going to try to transform it into a collection of numbers. So it has a little bit flavor of vectorization, but it's not exactly the same as the persistent image. Okay. And then now what they call it a structure elements, which is basically, again, a collection of numbers. And of course, in this case, they have some hyperparameter and so on. And we're going to see that very soon, what is going to be used here. So what is the transformation they do? Okay. The first transformation, which is slightly different, it's also rotation. So again, I'm going to rotate 45 sort of degrees. But the transformation they do is slightly different, meaning that I'm going to start with a birth death, but then I'm going to transform it as birth plus death and death minus birth. Okay. So this transformation is slightly different than persistent image transformation, but the whole idea is the same in terms of y-axis, is that I want to have points sort of in the y-axis corresponding to how important it is, so its persistence. But then the x-axis they happen to choose is birth plus death. Okay. So now the second step is going to do, it's kind of try to project those points, okay? So the projection it does has a very strange formula, but it also has some similarities. If you see this form, what does this look like?
Gaussian kernel?
It's a Gaussian, right? So again, the main idea is I'm going to rotate the persistent diagram, transform it somehow, and then I'm going to define this new transformation based on some sort of a Gaussian kernel, okay? So and they use the word projection, which is basically a transformation. The transformation is to say, I'm going to take a persistent diagram as input, and I am going to project it as a summation of a transform function. So what is this saying? This is to say that for every single point in the persistent diagram, I'm going to transform it by this function. And this function, again, looks like a Gaussian, but it's slightly different because I am actually transforming it into a single value, okay? So what did this do? This function takes an input, a pair of points, okay? And depends on the sort of the coordinates. What is x1? Remember, the points in the transform space is birth plus death and death minus birth. So the second coordinate, which is x1, the first coordinate x0, is a persistence. So this is the part that is also very similar to persistent image, is because I am looking at the persistence, and I'm going to look at the persistence in three categories. One, if it's zero persistence, no contribution, exactly identical to the persistent image. Then the second one is to say, there's a hyperparameter mu, or nu, which is, like sort of I want to do a thresholding. If it's within the zero between that threshold, it takes one form versus another threshold, it takes another form. Okay, so that's what this formula does. It's again, how it came up with this particular formula. You can read the original paper for it, but all of it, on the high level, it's again putting Gaussians over those points in the transformed persistent diagram, and depends on the persistence range, it's going to have a different contribution towards the final weight. Okay, so that's what it does. Okay, so why is this useful? Again, my conjecture is the exactly formula of this, well, it works because they can prove certain properties and so on. And I do suspect you can vary it a little bit and still achieving similar results, right? All that is based on is to say, I am going to rotate my persistent diagram, transform it in some way, and the importance of those points in contributing my final, what they call signature, or in this case, a particular value, has to do with its persistence. Okay, so that's what it does. So now once you do this, every single persistent diagram is now transformed into this value, which is what they call a topological signature. So the difference is, in this case, each persistent diagram is just transformed to a single value. So that's different from persistent image. Persistent image is transforming it into a vector. In this case, I'm kind of do a weighted sum of everything, and I'm going to transform it into a single number. Okay. So now, what do I have? So with this formulation, even though it's a little bit awkward formulation, you can prove sort of some stability, right? So with some conditions, if you have two persistent diagram, then remember this S, which is right here, you can say that, if I sum over the values of all the points in the persistent diagrams, then it's upper bounded by the Washington distance. Okay, so again, this is the Washington distance formulation. So it has some sort of stability. Okay, so again, if you're designing something like this, it's important to understand the mathematical property, especially stability, in order for it to be used for classification. So the takeaway from this slide is that, yes, under this formulation, there's some form of stability. So okay, so what does this do? I have some introduction to neural network, but oh, okay, maybe my slides is distributed over multiple slides. So in this case, maybe I have it here. Just a second. Yes, okay. So I want to emphasize right here is that once you have this transformation, what did they do? Okay. What they did is they can classify two things. One, they can classify images. Okay. So in these images, let's say it's handwritten letters. So what they can do is to say that, well, if this is my shape of my data, which is a letter N, let's say this is a handwritten one or it's a particular image, how do I get what they call the signature from this image? This is something they do is to say, well, in order to look at this image, I can define a filtration, right? I can define a filtration based on a particular height function. So I can define a height function this way. So then I can do a sub-level, say, a filtration of this shape. Or I can define a height function this way that, again, I can have a sub-level set filtration. And now with this transformation, each direction, I'm building my filtration on this shape. I'm getting a persistent diagram. And then the persistent diagram is going to give me a single value based on the previous formulation. And then this entire shape now, let's say each persistent diagram. So if I go through a circle of directions, right? That means, in fact, if I do a circle of directions, I get a circle or a collection of persistent diagram, which corresponds to a collection of values. So every single shape now, the signature became a vector, right? So what they can do is they can use that vector to do shape classification. So it's the same example here. This is sort of a high level. Again, right, this is a picture of, I guess, a turtle or something similar, right? You again, take different directions. So in this particular case, what they do is they take 32 directions. And also one detail that we didn't mention is that it's a 3-tuple persistent diagram. So what is a 3-tuple? That means I would like for each direction, I would compute its 0-dimensional persistent diagram, 1-dimensional persistent diagram, 2-dimensional persistent diagram, right? So it's like 32 direction. Each direction has 3 persistent diagram, which means it has a value of 3. So total, you are going to output this entire, you basically have a collection of persistent diagram which corresponding to an entire vector, and that describe a particular shape. And now if I have a collection of shapes, do I have a picture? I don't have a picture here. Let's say I have a collection of those shapes, then I can use those vectors as an input feature for my neural network, right? And then that is used for classification purposes. So in their original work, they reported on using this kind of vectors as classification, as an input to neural network to classify shapes and also to classify graphs. Okay. So because you can imagine for a graph, I can also turn it into a persistent diagram, which then turn into a particular value, and I can collect a bunch of values. Okay. So that is the overall picture of this piece of work. What I'm going to describe next is for folks who don't have a very good understanding of neural network. I was going to give a few minutes of introduction for neural network to better describe the architecture that is used in this piece of work. Okay, so what's coming up in the next lecture is once we have understand what is this sort of persistence-based layer in the neural network, the next thing is to move on to persistent landscape, which is a different way of vectorized persistent diagram, which also have its nice properties. And you can also use it for, again, classification and other learning tasks. Okay. All right. So any questions? Okay. So if there's no more questions, I'm going to stop streaming. And wait, somehow I can't stop it. Let me stop sharing.